Ace, a frontier. These are the voyages of the starship smAsho, our continuing mission to provide objective information, to seek out new information and new stories about astrophysics and cosmology and so on, even heliophysics, to boldly go where no one has gone before. And by the way, we're not going to spout a bunch of nonsense or misrepresent science articles if we can help it. So welcome to today's Cosmology segment. Fascinating stories once again. The give and take of megaflares from stars. How do they affect the planets? Do significant solar flares help planets form, or do they hinder planets forming? Do they push dense dust away from around the planet, illuminating the planet, or do they only take away its atmosphere? Well, the answer is we don't really know. But there are some studies going on with Chandra's X-ray telescope and so on. If you want to read this article, it's on phys.org in their astronomy and space section. So, super flares occurring more than once or once per week for each young star is part of this study. Anyway, flares have mixed effects depending on what the rest of the accretion disk around, I shouldn't call it an accretion disk, the rest of the disk of gas and dust surrounding a star. By the way, this region here is pretty interesting. You've got this novel shell-looking region, and then you got these bright areas out here. That one is about 13 light years in diameter, known as RCW 120. So planetary nebulas being studied here by the Chandra. Again, feel free to check that one out if you like. It's in the phys.org astronomy and space section. Now, we covered this story when it first came out, although it's back on the Science Wire, so we'll briefly talk about it again. Betelgeuse's dip in brightness. It was caused by a bunch of dust. Did the dust come out of the star, or was it just in the local environment? The answer is we ultimately don't really know. But it appears that the dimming was caused by dust. So here's a little animation of it, just showing you the different imagery of Betelgeuse over this period of time from 2019 to 2020, from a couple different sources there, and you can see the apparent change in shape and brightness and so on. Some people thought Betelgeuse was going to go supernova, and by the way, that would be one of the biggest natural events of our entire lifetimes, as if Betelgeuse went supernova, it would appear in the daytime sky for like 6 weeks, it's expected. By the way, Betelgeuse is also the largest object visible with the human eye, visible with the naked eye alone, that is. And you can find it in it's the right shoulder of Orion. And the belt buckle star actually points to it. It makes a perpendicular line, which points directly to Betelgeuse. It's very easy to find in the sky. It's a bright red star. Let's talk about more blistering stars. Rare insights into how supernova explosions affect nearby stars. Well, what do? They cause them to heat up. When a binary system's one star goes supernova, or I'll just say goes nova, as supernoval explosions don't seem to destroy stars, as when we look at the centers of all sort of nebular clouds, we see a star in them most of the time. In any case, this one's talking about supernova 2006 JC. And ultimately what they do is they cause the binary companion to get brighter and change their behavior a bit. I don't know why that would be surprising, but apparently it is. When a star explodes in a binary system, the debris from the explosion violently strikes the companion star. Usually there's not enough energy to damage the whole star, but it heats up the star's surface. Instead, the heat then causes the star to swell up, having a huge burn, like having a huge burn blister on your skin. The star blister can be 10 to 100 times larger than the star itself. So some interactions there between the dust expelled by the supernova, perhaps. And this one is on scitechdaily.com, I believe. SciTechDaily.com there. Blistering stars in the universe, rare insights into how violent supernova explosions affect nearby stars. Here's another nebular cloud. This is NGC 6888, the Crescent Nebula. It's NASA's astronomy picture of the day. And let me just check the life of the stream here and get off of your screen. So apod.nasa.gov is where you can find the astronomy picture of the day. The Crescent Nebula. And guess what's in the middle of that, folks? A star. Yeah, I know. It sounds crazy, right? Anyway, the fact is that we've never seen a star get born or a star die. And in any case, the central star in this one is a Wolf-Rayet star, which is a very special type of off of the beaten path sort of a star. It's not part of the sort of standard deviation of what stars do. Wolf-Rayet stars are massive blue supergiants. And our regular viewers may be aware of some Wolf-Rayet stars that we talk about regularly on the channel. NGC 6888 is in the constellation Cygnus, which is full of nebulae and located at about 5,000 light years distance. Again, if you want to look at the NASA picture of the day, the NASA astronomy picture of the day, it's apod.nasa.gov. Today, we're not going to pick a random generator number at all. We're going to look at the outputs of Cygnus X-3, which is involved with a Wolf-Rayet star. It also has an even more massive object orbiting it. I won't get into the astrophysics of that, but I just wanted to note the fact that Cygnus X-3, which is, by the way, the brightest intrinsic object visible from our solar system, is in an ultra-quiescent state. And typically what we see here is, before it goes into the loudest states, we see an ultra-quiescent state here. That was an extended period of quiescence there, which happened in 2006 or so. And you can see this extended period of very low counts of X-ray output. This is the X-ray output from Cygnus X-3. Again, it's a Wolf-Rayet star about the size of Mars's orbit, being orbited in a period of only 4.8 hours by a more massive object moving at relativistic speeds. There's a huge ionized disk of gas and dust in between the two objects. And at Lagrangian point 1, there is a increased ultraviolet output and so on. Anyway, it's one of the weirdest objects in the Milky Way galaxy. Cygnus X-3. And lastly, let's talk about the outputs of gamma-ray bursters. So one of the things that we see happening here in the jets is that we see the jet sort of oriented in this direction, and then a little portion of the jet oriented in this direction, as if it's bouncing back, or perhaps it's passing through magnetic shell regions. But in any case, perhaps check out this article on Eureka Alert. Space scientists solve a decades-long gamma-ray burst puzzle. Now, I'm not so sure if they've solved the puzzle, in that the mechanism that causes gamma-ray bursts is certainly still not understood. But the prediction was that the magnetic field in the blast waves becomes scrambled after the ejected material crashes into and shocks the surrounding medium. So we actually see the solar wind reversing directions like this also. And leave us a comment, let us know what you think. If you think it's the crossing of magnetic shell regions, or if it's some sort of a particle physics sort of interaction thing, or maybe it's electric. Who knows? As the entire universe is not electric, and neither are stars, but some aspects certainly are, such as your atmosphere, in that Earth's atmosphere is a capacitor between the charged potential medium of space and the charged potential medium of Earth. It's true, folks. The sky is positively charged and the ground is negatively charged. You're part of the bridge between the sky and the ground. So anyway, you may want to check out this one as well, titled "Space Scientists Solve a Decades-Long Gamma-Ray Burst Puzzle." And that's today's Cosmology segment. Thanks for tuning in. I've been your host, Dan, a.k.a. smAsho, signing off from Smash News Network. Least busted, name and news.